Good afternoon, everyone. Welcome to the EFG webinar, Responsible Mining for the Energy Transition, Cornish Lithium. My name is Vitor Correia. I am the Secretary General of the International Raw Materials Observatory, and I'm also the past president of the European Federation of Geologists. I will be the host of this webinar, which, by the way, is part of the webinar series that EFG is periodically organizing to foster the professional development of our fellows geologists. I'm happy to present today's speaker. In fact, I'm delighted. She's Rebecca Paisley, an exploration geochemist from Cornish Lithium. Rebecca has a PhD in Earth and Planetary Sciences from McGill University in Canada and a master's degree in Earth Sciences from the University of Oxford in the UK. She's specialized in using geochemical data to constrain subsurface processes in a variety of geological environments. And after internship with the commodity research at Roskill, she joined Cornish Lithium to assist with developing the geochemical side of the exploration efforts. Currently, Rebecca designs and implements the geothermal water sampling strategies for Cornish Lithium, and data collected from different sampling campaigns are used for resource estimation and prospectivity. She also manages the Cornish Lithium direct lithium extraction, evaluating different technologies and the abilities of these technologies to process the geothermal fluids. During Rebecca's presentation, you can propose questions using the question and answers function below in your screen. We will be selecting and answering those questions after the presentation. Rebecca, when you are ready, please.
So yes, thank you for inviting me today. I'm really excited to give the talk. I've thrown in a few more slides to kind of a shorter talk that I've given before to a couple of people in the UK. And what I'm hoping to talk about a little today is why we are having this energy transition, how is mining involved, obviously lithium and Cornish Lithium as a case study. And then a little bit at the end, just talking about the role of geoscientists and geologists and so on in this energy transition. So without further ado, we'll go straight over the company disclaimer and start with this graph, because I think ultimately the big question that we're trying to address with an energy transition is how do we mitigate for climate change? We know climate change is bad and there is a climate crisis going on. CO2 levels are the highest they've been in hundreds of thousands of years. And equally, mining says that we can help with the climate crisis, but mining has historically had a very bad reputation for rightful reasons often. But the industry says it's necessary, and so why are we discussing that? And so our role is in the mining industry and geologists in the mining industry is how can we address this climate change whilst retaining a 21st century standard of living? And so the answer is low carbon technologies, having a low carbon future. But in order to do that, we need a huge amount of raw materials. Because this clean energy transition, these low carbon technologies are ones that don't produce CO2 when they're running, but they also don't grow on trees. You can't grow a wind turbine on a tree, for example. You need to mine the raw materials for each of these technologies, and therefore this energy transition is going to be incredibly mineral intensive. And so I just thought I'd throw in a couple of examples. Wind power being one of the more obvious ones. In the UK, we get about 20% of our grid energy from wind power, although that's massively increasing all the time. But if you take a single 3 megawatt, wind turbine, then you're also looking at about 1,200 tons of concrete, 300 plus tons of steel, and a huge amount of rare earth elements and copper. And so, a 15 megawatt turbine, which would be enough to power a small town, would need even more minerals. If we then look at solar power, the UK at the moment gets about 6% of our energy from solar power. And whilst the technology used to be quite inefficient, later generations of this type of technology are really good for heating and or producing electricity. But again, solar panels, have polymers in them, made of glass, made of silicon, have copper, tin, lead, even silver in them. And again, we need to mine all of those minerals in order to make these solar panels. And so final example, obviously the lithium ion battery, which is essential really for the EVs and electric vehicles that the globe now are looking to make in the coming years and decades. Whilst the lithium is essential for an electric vehicle because it's or electric vehicle battery because it's allowing the charge to be distributed across the battery. You've also got your cathodes, which are made of your cathodes can be made of your electrolytes or your cobalts or your nickels, and your anodes are made of graphite, so a carbon. And each electric vehicle can have easily 10 kilograms of lithium in. So when you're making 90 million cars globally, about 18 to 20 million cars in Europe and about 1 million cars in the UK, you can see that we're rapidly going to need an awful lot of lithium. And we're going to need it very quickly. I just thought I would throw in this slide quickly to talk about it before I focus on lithium for the rest of the talk. I must admit I've stolen this figure from Dr. Eva Marquis at the University of Exeter, who's working on the Met for Tech project, which I would encourage you all to go dig into after this. But as you can see from this figure, humans have been using raw materials for obviously centuries and thousands of years, but as we've started introducing new technologies in the last couple of 100 years with steam engines, cars, planes, and now these low carbon technologies, the diversity of elements and diversity of metals that we're looking to mine is growing exponentially. And so we need to find these deposits, and therefore we need geologists working in the mining industry. So obviously I'm going to focus on lithium as an example. Lithium is considered a high impact mineral, and that's largely because it is dependent on one type of technology. So whereas copper is essential for a whole variety of low carbon technologies, as well as things that's already used in now, TVs, power lines, and so on, lithium is really dependent on this electrification of the automotive industry. And so much so that the World Bank, in fact, believes that the increase in lithium, cobalt and graphite ore for electric batteries could reach 300, 400, 500, possibly even 1,000% of their 2017 production levels by 2050. And that's all because of this rapid increase in demand for batteries for electric vehicles. The problem being that we could actually see demand start to outstrip supply as early as 2022. So when we look at this figure on the right hand side, you can see, I'm not sure if you can see my mouse, but if we take all of the unfinanced projects, so these are projects that are not even online yet, and we brought them online, you're still getting a gap between the demand for lithium, which is the blue line, and what could actually be produced, which is the bar charts below. And an even bigger problem is, on average, it can take 10 years from finding an ore body to mining an ore body. So this lithium should have been found in 2012, and the lithium in 2030, for when the UK and other countries across Europe decide that new cars must be electric, really should have been found last year. And so if we look at the current situation in the lithium space, most, although admittedly this figure is actually 4 years old, but not much has changed. The vast majority of the lithium that's produced worldwide either comes from South America, the lithium triangle, and these are lithium brines. So these are brines that are pumped to the surface and then evaporate over about 18 months before being upscaled and converted. Or you have spodumene minerals from Australia, which are being mined and then processed, often in China. And in fact, Europe has no manufacturing of lithium and lithium chemicals at the moment. The vast majority does happen in China or in Chile. and South America. And so what that means is that your current supply chain, be it your electric vehicle, if you've just bought one, your phone, your laptop, anything with a lithium battery, has started off its life in Chile or Argentina, likely been processed into a lithium chemical in the US or China, and then been put into a battery, potentially in the US or Southeast Asia and Japan, Korea or so on, and then been shipped somewhere else, maybe to Europe or the US, to go into the battery pack and then your electric vehicle and or your phone before it's actually been shipped to you. So that lithium could have gone as far as 50,000 kilometers before your electric vehicle has done 1 mile. And as you can see, this supply chain is heavily dependent on a lot of countries. The geopolitics involved, climate risks, supply chain risks are quite high. And so you would prefer for that to be localized, which brings us neatly into kind of the European lithium space. At the moment, there's no current source or production of battery grade lithium in Europe. We are solely dependent on imports from places like China. And yet we are ready to have gigafactories being opened across Europe, particularly in Germany, and a few up in the Scandinavian region and off towards Hungary. These gigafactories are being designed to support the automotive industry in Europe, and therefore we need to secure the supply chain for lithium and the other metals that go into these batteries very, very quickly in order to provide these gigafactories with locally sourced lithium, responsibly sourced lithium, and lithium that has a supply chain that's far more secure. And so if you have a more domestic supply chain by starting production of lithium minerals and lithium brines in Europe, you could be reducing your carbon footprint of that supply chain by up to 90%. You'd also be reducing your risk, so increasing the security of supply chain by not being dependent on as many products. If you can add diversity into the raw material by securing it from several places in Europe, for example, or from the UK, from Germany, and so on, then again you're making that supply chain far more secure, as well as reducing your carbon footprint and increasing the sustainability and responsible sourcing of all of your materials that go into your electric vehicles. And so, since I'm in the UK, I just thought I spoke about the UK example. This can clearly be scaled up even more so, particularly to the German automotive markets and others across Europe. The UK employs over 800,000 people in the automotive industry. So bearing in mind that the population of the UK is around 70 million, that's nearly, 1 in 100 or over 1 in 100 people, so 1% of the population. It has a turnover of about £80 billion a year. We produce over 1 million vehicles and 2.5 million engines. And yet the government has said that as of 2030, only new cars can be electric. So we will be phasing out these petrol and diesel new vehicles, which means that we as a nation have 9 years to completely change that supply chain from one that's designed around internal combustion engines to one that's designed around electric vehicles and the lithium-ion battery. So we need raw materials, we need upgrading processing factories, we need gigafactories, and then we also need the technology changes within that automotive industry in order to make those electric vehicles. Added complication for the UK is these laws known as the rules of origin, which have come in since Brexit. If 40% of any product has to be finished in the UK to avoid export fees, and given that the battery is actually 50% of the value of an electric vehicle, and the cathode is the biggest component of that 50%, you really need to be making your batteries in the UK to avoid these potential export tariffs. Because if I gave you a car that costs, £20,000 and one that costs 25,000 just because of the fees, you're never going to buy the more expensive car. And so in order to retain the automotive industry and keep it competitive, we need to be producing the vehicles here in the UK. And what that looks like from a actual material point of view is quite startling. You can see this is based on the Faraday Institution estimates. You can see that the demand for lithium, so LCE, lithium carbonate equivalent, by 2030 is exceeding 40,000 tonnes, whereas at the moment we're barely at 4,000 tonnes. So we need to produce some of this lithium here in the UK and also source it potentially from Europe and other places. Which easily brings me into Cornish Lithium and some of the work that we're doing here in the southwest of the UK. So we're a private company. We were founded in 2016 by our CEO, Jeremy Rathall. And as our name suggests, we are looking for the responsible extraction of lithium and other metals from Cornwall. We do this by first agreeing mineral rights agreements with different landowners over the county. This allows us as geologists to take a more regional approach into our exploration. And we've secured over 500 square kilometres of agreements. And actually, we're close to hitting about 30% of the county. We're currently a private company, although that will likely change in the next 12 months. And so far, we've raised funds through shareholders, a series of crowdfunding events, and also government grants, which we look to utilise to improve the research into both exploration and extraction of lithium from different materials. And so why are we looking for lithium in Cornwall? Well, Cornwall has over 5,000 years of mining history. These 4,000 known mines, but it's particularly well known for the mining of tin and copper back in the 17, 18, 1900s. And in fact, this figure on the right is the mining that was happening here just 200 years previously. And the county now is very dependent on tourism as an industry, as the final mine closed in Cornwall in 1998. And whilst China clay is still extracted in regions of the Cornwall, that industry is also declining slightly. And so why is Cornwall good for lithium? Well, we have a lithium-enriched granite batholith, one of only 5 worldwide, that underlays most of the county. So all the way from the Isles of Scilly, which would be around here in the southwest, all the way up to Dartmoor in Devon and Cornwall. And it's actually exposed at the surface in 5 or 6 locations: Land's End, Carmanellis, the St Austell region, Bodmin and Dartmoor. And we're particularly interested in this lithium in the G4 and G5 granites, so these orange ones and green ones, and you can see them outcropping in the St Austell region here, because they are the ones that have micas that are most enriched in lithium. And so these mica minerals can have up to 20,000 parts per million lithium. So that's where our lithium is originally coming from, potentially. Why is it also found in waters in the southwest? Well, the area, because of that giant granite batholith, also has a very high heat flow, one of the highest heat flows across the country. And that's because the granite is also full of uranium and thorium and potassium and so on, so sources of heat, which is heating up groundwaters that are circulating through very large mineralized structures. So in Cornwall, you have 2 major structures or sets of structures. You have cross courses that go north-south, and you have lodes that go east-west. And these lodes were or are the mineralized structures that were mainly mined in the 17th, 18th, 19th century for the copper and tin. And then the north-south ones are large county crossing structures that related to periods of extension and compression. And what's happening is you're getting these waters flowing through these structures. The water is hot and you're leaching lithium from the granite over time. So much so that lithium was actually observed in these structures back in the mines when they were being operated on. So in 1864, a sample of the waters from the mines that were flowing into the shafts from these structures was analysed in London. And to paraphrase, he Professor Miller, he said, we have so much lithium, if only we had a use for it. And that's because in 1864, there was no use for lithium. The lithium battery was only commercialized in 1991, and the last mine in Cornwall, as I said, closed in 1998. And so there's been no real overlap between exploring Cornwall for critical metals, the mindset of providing these for modern technologies, and the mining industry being active in Cornwall. Which brings us directly into our exploration work streams. So we have 4 major exploration work streams. We have our hard rock lithium, which, as I mentioned, is looking for these microminerals and understanding the distribution of those within some of the exposed granite areas in Cornwall. And we have 2 geothermal work streams. We have our shallow geothermal, where we're looking at waters that are circulating in structures at about 2,000 meters below the surface. Then we have our deep geothermal, where we're looking at waters that circulate up to 5 kilometers. And then, as I mentioned before, because of the way we're doing our exploration, creating a 3D digital model of Cornwall and taking a regional approach, it's impossible not to find new potential copper, tin, zinc, lead, tungsten deposits, and so on. And so we do keep an eye on those kind of opportunities as well. And so how do you go from this historic mining exploration all the way into 21st century exploration? And the big questions that we're trying to answer within our technical team is, where is the granite and where are the structures? Because that's where I'm going to find the lithium. And we've started this by actually using all of the historic mining records that we have across Cornwall. We have access to a huge host of private collections, as well as many of the public works. And we have 2 full-time digital archivists who take these old mine workings and copy them, so we have digital copies. So we can take these mine plans, we can then digitize the structures. And then when you start doing that in 3 dimensions, you slowly build up a 3D map of the structures below the subsurface without ever having to drill. And in fact, this level of detail was enough for us to drill during our first 2 boreholes, and we hit the structure that we were interested in, actually plus or minus 10 meters where we thought it was going to be. We then use modern techniques to complement this historic data. So we use satellite data to understand where the structures can be outcropping and their major orientations. We can then put these into machine learning algorithms to pick out subtle structures that you wouldn't necessarily pick out by eye. We can then combine that satellite data with historic mapping and bathymetry data for structures that are offshore. We can use aerial surveys to look at the alteration of rocks. So in Cornwall, there is very minimal actual rock exposure, but there's an awful lot of alteration and exposure at cliff faces. And so we can use aerial surveys to look at that and see how some of the minerals vary. Alteration being a key indicator for fluid flow, which is obviously something that we're interested in. We can also do digital elevation models, so DEM models, with those drone and aerial surveys. And by creating these 3D maps, we can then do some virtual field work and use structure from motion programs to take strike, dip orientations and so on of structures that you physically wouldn't be able to get to. And we can then project that inland, so we have a better idea of what's going on in the subsurface away from the coastline. We're also trialing a lot of different virtual reality fieldwork softwares, this figure being an example of one of our geologists, Ali, looking at how you can map structures around, well, Lulworth Cove, which is in Dorset, but looking at a similar process for Cornwall. Also geochemistry, so we have a huge amount of historic geochemical data, both from mines and from the surface. And there's a lot of public data sets as well, looking at soil, water, sediments, and so on. So part of my job is understanding the anion signature of some of these waters and understanding the mixing relationship between mature waters that have high chlorine and high lithium concentrations with meteoric waters that are slowly percolating into the ground. We can also use soil data to better understand the subsurface geology. So I've just got 4 examples here from a TELUS survey, which is a publicly available data. We can use vanadium, for example, to pick out the granites where there's very little vanadium versus some metasediments and some sedimentary sequences. Use copper to obviously pick out the areas where you get a lot of lodes and a lot of mining or ex-mining. Calcium is picking up the lizard, which is an ophiolite sequence in Cornwall, and cesium, which is picking out granites. And so part of my day job is using all of these different data sets to figure out what's going on beneath the subsurface before we go and drill. So I'll give a couple of updates just on all of the different work streams, and then also obviously happy to answer any questions on them later on. We're just going to focus on the lithium ones, the lithium hard rock and geothermal today. So our hard rock exploration, we're drilling or have been drilling in the St Austell region of Cornwall. So this is known as the China clay region, and in fact you can see it from space if you look on Google Maps and type in St Austell. We've done 2 drill campaigns, which are now being kind of finalised in a mineral resource estimate, which will hopefully be out, particularly, well, definitely by the end of this year, hopefully in the next few weeks. This will be a JORC compliant resource, and we'll be looking to then use this for the basis of our pilot plant demonstration and slowly bringing this system online into production. The great thing about St Austell is the area has a huge amount of pre-existing infrastructure. You've got railways, you've got ports, you've got a lot of industrial units that are now being underutilized because the China clay industry is declining slightly. And so we can build on these sites, these brownfield sites, to reduce our carbon footprint when scaling up our production in the area. And responsible exploration is not the only essential thing. You also need responsible extraction. And so we, after a series of different test works that happened in the last 2 or 3 years, have signed an exclusive license for the St Austell region with a company called Lepidico, who are from Australia, for their hydrometallurgical process, looking at making lithium hydroxide from the micas that are found in Cornwall. What's great about this process is it doesn't require any high temperature roasting like you need for spodumene, which is reducing its environmental impact, and lower cost because you're not having to do anything at very high pressures and temperatures. We'll be drilling and utilising the existing China clay pits. So this is reopening an already open mine. So again, reducing your carbon footprint and environmental loss there. And we'll be looking to potentially use waste heat from other processes in the Cornwall within our flow sheet. So again, reducing any carbon footprint. And test work that we've done in the last 2 years has successfully produced battery grade lithium hydroxide at over 90% lithium extraction from the mica minerals. Then if we can move on to our geothermal water exploration stream, which is kind of my day job. We have 2 research boreholes that went to about 1100 meters and 830 meters in the St Day region of Cornwall. This region was once the richest square mile in the world because of the amount of copper and tin being mined there, but it's now one of the poorest areas in Europe, and that's because mining left back in the 1900s. So we drilled these 2 proof of concept boreholes to see if these lithium waters were still circulating in the subsurface. We successfully hit a whole series of structures, including one, our main structure, within 10 meters of where we expected it to be. We isolated these structures with a system known as a packer, which is kind of a balloon on a stick. And you put it down and then you inflate it, and you can bring water up from these structures without diluting it by your drill muds and so on. We tested the waters, found really high fluid flows and values that were in line with historic data for the region. There's really very few contaminants in the water, so that's great for processing. And now we've developed this area as an extraction test work site, so an R&D geothermal test facility, where we will be bringing companies to site to test their technology on the geothermal waters. We're also looking at doing kind of pump tests and various things in the coming year to understand how we can develop and estimate the resource, lithium resource in the region. The area is a fractured granitic basement, so it's not a sedimentary sequence that's easy to model. We are also looking at deep geothermal. So this is in conjunction with a geothermal energy company down here called Geothermal Engineering Limited. And what we are looking at there is their 2 boreholes, which they've drilled to 2.5 and 5.2 kilometers, one being an injection well and one being a production well. We analysed the fluids from the production well and found them to have globally significant lithium values, so over 250 parts per million. What's really interesting is that the dissolved solids, so all of the other stuff, is actually lower than seawater. In comparison, the geothermal brines that you'd say find in Germany can have 180, 200 plus parts per million lithium, but are 4 times as salty. So they've got more other things in that you need to get rid of before you can process it. As part of this work with GEL, we have a joint venture called GeoCubed. And this project aims to commission a pilot plant for lithium extraction on our test site by March 2022. This is funded by the LEP, which is the local authority here in Cornwall, for a sum total of about £4 million. And we're hiring over 10 people for that project. We'll be looking to keep them on full time after the project is finished. And so whilst we are looking for lithium there, we are also looking at the potential for co-production of geothermal power or geothermal heat, and in fact, any other metals that are of significant quantity in the waters. And so I thought I'd just put a few slides in on responsible extraction of lithium from geothermal brines. Thought this was particularly relevant given the number of geothermal projects that are potentially coming online in Europe as well. It's also my day job, for the most part, is understanding some of these processes at the moment. And so if I was to give you a current brine at the moment, it would probably have come from South America, Chile, Argentina, and so on. And the first step of their processing of those brines is actually to evaporate. So this figure on the right-hand side is one of the evaporation ponds in Chile, just next to the Atacama, or in the Atacama. But these ponds can be, 10 kilometers across, 5 kilometers wide, and the water sits at the surface in these ponds for up to 18 months as it goes through different stages of evaporation, slowly concentrating up the lithium and slowly taking out some of the byproducts such as calcium and magnesium. But unfortunately, you can't do this in Europe because it rains far too much, not dry enough and not hot enough. And so that's when direct lithium extraction, or DLE, comes in. So DLE is all about taking lithium straight from the brine. So rather than evaporating the water off and getting rid of the other elements, you're looking at taking just the lithium and keeping everything else in the water. And you can do this through membrane technology when you're filtering the waters, or sorbents and ion exchange type technologies where you put water through columns and the lithium attaches to beads that have an affinity for lithium. All of the other elements flow through the columns, and then you can strip the lithium off, often using an acidic material, or you can change the temperature and strip the lithium off that way. And so this makes geothermal plus lithium possible, and that's why you're seeing a lot of potential for these projects in Europe as this DLE technology develops. The great thing about DLE is the potential for it to have a far lower carbon impact than any other form of lithium processing that is online today. That's because you can bring geothermal waters up from depth. So these waters can be 150, 200 degrees. You can use that heat, convert it to geothermal power using turbines, or so on. You can then take your slightly cooled water, potentially put it through other heat transfers and so on, use that green energy to take the lithium out, and then you can re-inject back into your reservoir. And so by doing that, you're generating excess power potentially that can be used in green homes. You're using the heat, which can be used in some of the extraction steps. Your footprint is very minimal because you're not having to have water up at the surface. And so your overall, and you're one last thing would be your freshwater use is far lower than other processes. And so it's very green, and one way of looking at these types of technologies and their overall impact are life cycle assessments, which I wasn't going to go into details now, but I would encourage anyone who's interested to look at them later on. So far shorter processing times, getting your lithium quicker and in a far cleaner way. And so that was most of what I had to talk about with lithium today, but I thought I'd just take a step back because the talk was entitled Mining and the Energy Transition, but what's the role of geoscientists, geologists, geophysicists, geochemists in that transition? You know, our roles are to undertake responsible exploration, develop these responsible extraction methods, and embrace these new methods that I've mentioned, such as life cycle assessment, ESG, environmental, social governance, and social license to operate are also big buzzwords at the moment, but have very positive meanings. And it's something that a lot of companies are embracing. We're also, as you can see, we're using a lot of digital 21st century data scientist methods, so artificial intelligence, machine learning, and so on. And I think utilizing this digital revolution is helping companies find new projects and innovative ways of bringing them online. And I've had across all of my slides in the corners little figures that had numbers from 1 to 17, though they were very small admittedly, so I don't blame you if you missed them. But they are the UN Sustainable Development Goals. Mining can touch all 17 of these goals. And these goals are socioeconomic or environmental targets that look to have a kind of positive impact on the planet in one way or another. So, for example, if you're creating geothermal power, you're looking at creating affordable clean energy. So that's target 7. Equally, if you're bringing a huge amount of investment into a community, you're likely improving the quality of education in that region, reducing poverty, and creating sustainable cities and communities. And so mining, as I mentioned, can touch all 17. And actually, geoscientist roles in the even wider industry can touch all of them. And I often use this figure in careers talks that I give, but actually I've decided to keep it in for this talk because I'm aware that there's probably quite a broad range of geologists on this call. And I thought it would be interesting just to throw it in there if anyone has any questions. I think it's a really good way at looking at a type of career and the potential impact that you can have on society. So obviously mining and mineral resource estimates are down here in the bottom. Geothermal energy being another one, that's my day job. But equally things like science, policy, NGOs, and environmental geochemistry, renewable energy, or everything can have an impact and a positive impact, which links back to the energy transition and trying to retain that 21st century standard of living whilst having as minimal impact on the environment as possible. So my summary points for this talk, I hope, were there's a climate crisis and it's resulting in an energy transition, which is requiring an uptake of all of these really new technologies, be it wind, solar, electric vehicles, and so on. But in order to make those technologies, we need far more critical metals than we've ever been mining before. And therefore, the mining industry is essential for that transition. Obviously, I work for Cornish Lithium. I'm very interested in lithium. And lithium is required, particularly for the electrification of the automotive industry. So as we go into making lots of EVs, the entire supply chain needs to adapt to that, and it needs to adapt to it quickly. And then as a geoscientist, we seem to have found ourselves in a fundamental role of finding these materials and actually extracting them in a responsible manner. And so that's the end of my talk, but I'm more than happy to answer as many questions as possible in the time that we're allowed.
Well, thank you so much, Rebecca. I mean, the topic is a fascinating one and your presentation was brilliant. So thank you so much. I'd like to invite everyone to put your questions on the question and answers button below. And we have already several questions, Rebecca. The first one is about minerals legislation, and reading the question, it's about who owns the mineral rights in the mineralized brines in the UK. And I'm wondering, is this what is keeping Cornish Lithium back? I mean, why aren't you already producing, assuming that there is a demand?
Now you sound like my CEO.
Sorry for that.
So the mineral rights in the UK are probably the most complicated anywhere in the world, because gold and silver are owned by the Queen. Oil, gas and coal are owned by the state, so that's the government. And then everything else is owned by the landowners. The problem being that the land ownership has changed, obviously, through time for over thousands of years. And the mineral rights can be split from the landowners. So in Cornwall, where you've had, 200, 300, 400 years of mining history, sometimes you can find that, John Smith owns 1/16 of the land of the mineral rights in this area, and then someone owns 5/10 of the mineral rights in this area. Also in Cornwall, there's a lot of big family kind of land ownership families. Some of them have won their mineral rights in games of cards in the 1800s. They were betting their mineral rights. And so, we've spent the first 3 or 4 years of the company was largely actually securing mineral rights agreements in enough locations to give us an area that we can actually explore for. So whilst we started in 2016, we didn't actually do our first drill campaign until the very end of 2019, 2020. We actually finished our campaign, our first drill campaign, in March 2020, and I'll let you guess why it finished in March, because COVID got in the way. And so we're looking to drill at a new site next year to continue to explore for these brines.
But these brines, this minerals right approach also applies to brines, because brines you can have a borehole drilled there and it's just sucking the brines from everywhere around.
Yeah, so you can also have mineral rights for the hard rock and mineral rights for the brines. So in a couple of places where we've been drilling, actually it's a great example, the current site, one company, Cornish Metals, owns the mineral rights for the hard rock, and we own the mineral rights for the brines. And so when we drilled and hit an 8% copper load, they then raised £6 million off it and drilled in 6 locations to find the copper. So it's very complicated is one way of putting it.
Okay, that's interesting. A second question is about contaminations, and I believe this raises the environmental and also the public opposition issues. So the question is, are there any identifiable metal contaminations from the exploitation of lithium on the groundwater and on the land?
That's a good question. No, is the short answer. These waters are very benign, almost groundwater with plus lithium. They're pH neutral. We're drilling in such a way that we are drilling far below the mine workings in Cornwall, which would have, acid mine drainage problems that are being processed separately. And so, yeah, there's no major contaminants of any kind really in these deep waters. The elements, elements like arsenic and copper and all of those kind of normal contaminants are not present in high quantities at all.
So I guess this is good for public acceptance of mining, right?
Absolutely, absolutely. People in Cornwall anyway are very excited about the prospect of mining coming back, be it hard rock or with brines. And we are obviously keeping on top of the understanding the chemistry of the brines and any environmental impact it could have. But so far, everything is good.
Okay. Another question I have is about the resources estimation. I mean, you mentioned that you are using a JOR compliant approach. And the question is, why not a PERC compliant approach? So the European code, which is also CRISCO aligned.
So we're using a JOR compliant resource approach for our hard rock mineralization, which I must admit I'm not involved in on the day-to-day. So I'm only mentioning what I've been told. We have a few Australian partners that we work with on the extraction side, and also some of our executive team have worked in that. So that's why we've gone with a JORC approach for that. For the brines, it's not an easy question to figure out the resource. We've had discussions with the boards of JORC and other people to actually discuss how do you do it properly and how do you do it robustly, because there are very few resource methods out there that I think will actually be able to be used for this. So yep, the European one, I believe actually someone sent me the outlines in an email a couple of months back, as they were looking to adapt it. And so that, again, that's something that we'll be looking into as we do some long-term pump tests to figure out sustainable pumping rates. So it's not an easy process by any means, and that's because the resource is not a single bed of sandstone with lithium or anything like that. It's a series of fractures joined up, unknown quantity of fractures and unknown quantity of mixing at the moment. But we're building discrete fracture network models, stochastic modeling using statistics and various other machine learning and AI type techniques that combined will be able to give us a better idea of the resource.
And I'm sure the people in the park will be delighted to have this challenge. Almost some of them are attending the meeting. Another question we have is about the DLE process. I mean, and the question is, what are the best sorbent materials for the lithium extraction?
Someone asked me this half an hour ago. I wonder if they just signed up to this talk. Again, that really depends on the brine that you're dealing with. So if you took a brine from Cornwall, a brine from Vulcan, and a brine from the Salton Sea, they're all completely different. And the sorbent that would work best for each is completely different. We're also looking at some more innovative and out there type techniques that aren't dependent on sorbents in the same way. And we find that certain sorbents work particularly well, and other more traditional adsorption technologies do not. But the IP of which is the technology providers, and then there would have to be some kind of secret to act NDA for everyone here to give me the lowdown of what we've been doing for our research. But we've tested at least 24 types of technologies, I'd say.
Rebecca, another question is on CO2 footprint. Is there any idea on the CO2 footprint of this DLE method?
We've done a very high level life cycle assessment comparison between a spodumene project, a brine project, and a geothermal project, and a micromineral deposit, just to see how much better geothermal plus DLE would be. It is significantly lower, but because we did that with a whole series of assumptions, we don't have a pilot plant running for 2 years consecutively to add in all of the variables. We do have quite wide error bars on that, but you're looking at, well, in some cases, some have claimed that they could make 0 carbon lithium, and whilst we know ours would be very low carbon, I wouldn't want to put a number on it just yet because we haven't defined every input into the model. But
it should be low.
It will be low.
Since we are approaching the end, just 2 quick answers on 2 topics. One is seismicity. So are there any seismicity problems? And the second is about the mica minerals. People is asking if we are talking about lepidolite or other types of minerals.
The seismicity, we haven't had any seismicity issues for our shallow boreholes. I believe the geothermal company who drilled the deep ones had a little bit at one point when they hit a fault and were doing some injection tests. For that, I would encourage you to look at Geothermal Engineering Limited online. And then on the micas, I'm probably get fired for not knowing the mineral, but I believe it is, it's zinwaldite is the main mineral that we're looking at. But if you want to understand more about the mica minerals found in Cornwall, look up papers by Beth Simons. 2016, 2017. They look at the fractionation of lithium and various other things and define the granites in the region in Cornwall. So I will point you directly at those papers.
Thank you, Rebecca. Some colleagues are also saying that the granites in Cornwall are also have enrichment in cesium and rubidium, which might be also present in the brines.
Yes.
They are a problem, or they are a
no,
resource?
they are a wonderful challenge. Let's put it that way.
Okay, it's good news. So, Rebecca, thank you so much for delivering this beautiful presentation about a fascinating topic. I believe more people will be looking to this webinar on the YouTube, because it will be posted live. So, thank you to you. Thank you also to the audience. I mean, for taking time to be here with us. We had more than 55 people attending, so it's good to see that this geoscientist community is alive and interested in the topic. Let's keep in touch. Bye, everyone.